Hello, Southwestern Region members. Thank you for viewing Pete Lindsley's and my presentation about streamflow measurements and their application to Fort Stanton Cave hydrology. What I'll be talking about today is the utility of streamflow measurements for cave hydrology studies. I'll give these. I think these measurements are useful for cave hydrology studies in general, but in particular at Fort Stanton Cave. I will review the basic process for making streamflow measurements, and I'm going to give some example applications that we've done at Fort Stanton Cave. And finally, we are trying to recruit some careful workers to become part of the team making streamflow measurements at Fort Stanton Cave. What is the utility of streamflow measurements? Well, in general, what I'm going to be talking about today is we can use these measurements to quantify the exchange of water between surface water and cave streams, which of course only applies to caves with streams, such as Fort Stanton Cave. And then we can combine stream discharge measurements with stage-only data from pressure transducer data loggers to calculate flow volumes. And if point number 2 doesn't make sense as you listen to it now, that is a part of my talk today, and I hope by the end of the talk this is something I want to explain a lot more clearly. Finally, I think there's other applications of stream flow measurements to cave hydrology, and they are limited only by your imagination. I'm going to define some terms here up front. Frankly, some of these terms are just hydrology jargon. The first term is discharge. That is the volume of water flowing past a point on a stream per unit of time. In the United States, that's commonly expressed as cubic feet per second. That is how many cubic feet of water are going past a point every second. Another term I'll use a lot is stage. Stage is the elevation of the water surface in a stream with respect to an arbitrary reference height, a datum. Intuitively, we know that the height of water in a stream is higher at higher flows. As the stream flow decreases and eventually goes to zero, logically you might think the stage when the stream is dry, the stage is 0 feet, but surface streams with alluvial channels change constantly, and zero flow might happen at different heights. That's constantly in change. And finally, the datum, the zero datum in the stage is set so that the stage is never zero. It's always a positive number, because sometimes we use the stage in calculations, in logarithmic calculations, and we don't want to try to take the log of zero. You can't do that. So here is a little diagram that kind of illustrates some of the main points. What we see here is a cartoon representation of a stream. The water in this stream is coming out of the page. Here's the width of the channel, here's the depth of the channel, and the water coming at you is coming at some velocity. So to make a discharge calculation, we define discharge to be width times depth times velocity. The units of width are length, the units of depth are length, and the units of velocity are length per unit time. You multiply all three of those together and you get discharge as length, cubic length per time, and in the United States, again, that's typically cubic feet per second. That seems pretty simple. Why is there any complexity to this? Well, yeah, of course, the real world is a lot more complicated. Here's why the real world is a lot more complicated. The depth in a stream is not a constant. Of course, it's shallower near the banks quite often, and the velocities aren't constant. The velocities tend to be higher in the middle of the channel and lower near the sides of the channel where the water is slowed by friction. Also, if we look at a stream in a profile, a side view, we see this is the distribution of velocity in profile. The water near the surface tends to be moving at the fastest. The water near the bottom of the stream tends to be moving slower, where the water is slowed by friction with the bottom of the stream. So the velocity distribution is not uniform in the vertical as well as in the horizontal. And in the real world, streams often can look like this. They can be very chaotic. There's eddies, there's whirlpools, there's backwaters, there's turbulent flow. Measuring stream discharge at a location like this would be nearly impossible with most technologies. So so how do we deal with the real world here? Well, what we try to do is find a stream section with, if we go to a stream that we want to make a measurement, and we try to find a stream section with a relatively straight channel, and we hope the velocities are relatively linear and pointing down the channel. When you make a stream discharge measurement in the real world, often the first thing you do, if you've never been to the site, is you look around for a stream section that has a nice uniform straight channel. So then how do we deal with the differences in depths and velocities at the various locations in the stream? Well, we divide the stream into subsections. And when I say we divide it, we don't physically divide it. What we do is we go across the stream and make velocity measurements at different points across the stream. And we measure the velocity at each section. We measure we assign a width to the section we're measuring. We measure the depth, and we compute the discharge for each one of these subsections, and then we add up the subsections across here to get the discharge for the entire stream. Vertically, how do we deal with the different velocities? Well, here we are at our diagram that shows a stream velocity distribution in profile again. The velocities are highest near the top of the stream and lower near the bottom of the stream. And it's been determined experimentally using laboratory experiments and in many streams that the best place to measure the velocity is at about the 0.6 depth. And here's what I mean. The average velocity of a small stream is, you can see that it's thought to be it has been experimentally determined in small streams to be at a depth of about 0.6. That is, if the stream is 1 foot deep, the average velocity is generally thought to be represented by setting the current measuring device, the velocity measuring device, at about 0.6 depth. So how do we measure stream velocity? Well, there are many instruments for measuring stream velocity. I'm going to only discuss one today, and that is the type of instrumentation that we use at Fort Stanton Cave. It is a current meter outfit. That is all the equipment you need to make stream discharge measurements. The outfit is owned by the Bureau of Land Management, and the Fort Stanton Cave Study Project is the owner. The device on the left here is a current meter. It is a vertical axis current meter. There is a bucket wheel mounted on a vertical axis here. It's very similar to an anemometer you would see at a weather station used to measure wind velocity. The bucket wheel is designed to work underwater, and the bucket wheel spins faster as the velocity increases, and a device that counts the revolutions, calculates the velocity, is attached to the bucket wheel. This device on the right is called a wading rod. You use it, the current meter is attached here. The wading rod is placed on the bottom of the stream. The stream comes up to some depth. These increments that you see here are 1/10 of a foot apart, so you can read the depth very easily off the wading rod. And in order to put the current meter at the 0.6 depth, there's a bit of clever engineering up here that makes it very easy. Once you read the depth on the wading rod makes it very easy to set the current meter at the 0.6 depth. Here I am measuring stream discharge at Government Spring. What I've done here is I've stretched a tape measure across the stream. I'm moving across the stream with the current meter attached to the wading rod, making measurements at different intervals as I move across the stream. This current meter is making the velocity measurement, and I'm keeping track of where I'm making the measurements. Here is a stream discharge information from an actual stream measurement that I made at the Rio Bonito at the Fort Stanton Fieldhouse on May 4th, 2019. This upper graph here shows the velocities as I'm moving across the stream. Looks like I was making measurements at half-foot increments. As I moved across the stream, you can see that the velocities in the middle of the stream are relatively uniform between 1.5 and 2.5 feet per second. This is actually a really good section. And this lower diagram shows the depth that each one of these corresponds to the measurement above it. This is again a really nice section. The depths are really relatively uniform, around 1 foot. Here's where the current meter was located at 0.6 below the water surface. And so I'm moving across the Rio Bonito making velocity measurements. Here's a summary of that, a compilation of that very last measurement. Don't try to read the numbers here. What I'm showing you here is the location as I moved across the tape measure. These are the marks on the tape measure. Here are the depths of the stream. Again, they were really very close to 1 foot, just by pure coincidence. Here are the velocity measurements at each of those sections. This is the flow, the actual cubic feet per second in each of the subsections that I divided the stream to. And we can see on that day, at that time, this total discharge was about 21.5 cubic feet per second going past the Rio Bonito bunkhouse at that day. All right, let me give some examples of how we've applied stream flow measurements to Fort Stanton Cave. The first I'm going to talk about is the first couple of examples I'm going to show are exchange of water between surface and cave streams. Here is a Google Earth view of the area around Fort Stanton Cave. I'm sure most of the people that are listening to this are familiar with this general concept. Here's the entrance to Fort Stanton Cave, Government Spring, the Snowy River Passage going off to the south west, Little Creek, Eagle Creek. Prior to this study that we did in April of 2016, it was known that Eagle Creek was losing flow in this section here. And so what several of us did is we walked along Eagle Creek with a current meter and made measurements of the discharge going downstream. And here's the results of that study, again in April of 2016. As I made measurements going downstream, you can see that going over the course of about 2 miles, 10,000 feet, the stream discharge went from 2.5 cubic feet per second to less than half a cubic foot per second. Is this the source of water for Snowy River? Well, it's likely that it's at least a component of it. So we have a good documentation here of the water going into the stream bed. There are small swallow holes along here, but most of the water is just going down into the gravel and disappearing. Here's at the other end of the Snowy River system. This is a Google Earth view above the discharge end of the Snowy River stream. Here's the Rio Grande, the Fort Stanton bunkhouse in this area here. Here's the Rio Bonito. These little pins represent discharge measurements I took along the Rio Bonito down here towards Government Springs. ignore my little shorthand here for the measurement points. Steve Pearman made me aware that many years ago Buzz Hummel had injected dye into the Rio Bonito in this general area here, and some of the dye showed up in the main corridor in Fort Stanton Cave. Well, my goal here was to walk down the Rio Bonito and see if I could find the insurgents using the stream flow outfit, the stream discharge measuring outfit. And here are the data. This first point here represents the Rio Bonito at the Fort Stanton bunkhouse, and I was walking downstream making measurements as I went, and this is the area of the suspected insurgents right here. Well, my first measurement was about, I don't know, looks like about 4.6, 0.7 cubic feet per second. Just above the point where the insurgents was inspected to be, maybe a little change. And then on the next measurement, as I was working my way downstream, it seemed like the discharge decreased. And I thought, oh boy, maybe this is the insurgents. But the very next measurement, the discharge started climbing back up, and pretty much by the time I'd walked down to Government Springs, most of the measurements were greater than 4 cubic feet per second, except for this one here. So what's happening here? Well, each of these measurements has some error associated with it. If we make a stream flow measurement, a really good one, we say has got a 5 to 10% error associated with it. If we're not in a nice straight channel with uniform flow, the measurement error can be much higher. And that may be what happened here, is that this measurement here just had a larger error associated with it. Do I see anything here that I would call an insurgence? I don't. These could be just normal measurement errors. Another possibility is hypereic flow. You've all walked along a stream and seen the water sink down into the gravel next to the stream, and it pops up again a little bit later. That's called hypereic flow. So is there an insurgence here? Well, not that I could say definitively on this particular day and time. Is it possible there is an insurgence there? Sure. This was actually, the Rio Bonito was actually at a relatively low flow here. It's possible at higher flows the water does go into there is an insurgence, and the water shows up in the main corridor. And the other application I'm going to talk about today is using discharge measurements with stage-only data from data loggers to calculate flow volumes. Here's a picture of the Snowy River passage, and the big blue dots here represent data loggers in the Snowy River stream. Here, let's see. And here is an output from one of the data loggers. The red graph is temperature, and the blue line is the stage data from the pressure transducer data logger. So we can see that in the fall of 2019, the water depth here, the stage, was 0. There's no water in the stream. And somewhere around start of December, water showed up in the stream, the stage went up, went down a little bit, came up again, and peaked here around March of 2020, and the stage gradually declined, and we went back to a dry channel somewhere around August of 2020. So this tells us the stage, but it doesn't tell us anything about how much water this represents. It's just the stage. We have no idea what volume of water this represents. So how do we turn stage-only data into volumes of water? Well, the way you do that is you make a stream discharge measurement at a point where there is a stage data recorder, a pressure transducer data logger. This is Talon Newton and I making a discharge measurement at Snowy River at SRS 15. How do we take that data and turn it into calculate flow volume? Well, what you do is you make, and this is not from a cave stream, this is just an example surface water stream. We plot discharge on the x-axis, stage on the y-axis, and we see as discharge goes up, the stage goes up. Each of these diamonds represents a stream discharge measurement that was made with a current meter and current meter outfit, and we connect the dots in this case with a log Pearson type 3 distribution, and anywhere we know the stage, we can come out here and compute the discharge. We can estimate the discharge. How does this work in the real world? Well, this is, again, not a cave stream, but it's one relevant to Snowy River. This is Eagle Creek near Alto, New Mexico. The data on this upper graph, this is the gauge height, which is stage. This is just another jargon term for stage. And we can see the different flood events coming through here over the course of a year. The stage goes up as the discharge increases. Well, down here, we see a graph that the USGS has calculated discharge in cubic feet per second from the gauge height data. And if you look at these two curves, they look remarkably similar. This one's plotted on a logarithmic scale. The discharge is on a logarithmic scale. The gauge height is on a linear scale. But if you look, the data are remarkably similar, and that's because we take the stage only data, which are recorded at 15-minute intervals. You use the stage discharge curve to compute discharge at every location, at every point in time. So this instrument is recording stage every 15 minutes. Well, discharge measurements are very labor intensive and time consuming, and you only have a few of them. But if you build a successful stage discharge curve, you can go from stage to discharge at 15-minute intervals. So it would be possible to know, if you wanted to know how much water was going down in the stream at any time, or the total amount of water that has gone down the stream at a particular interval of time, you can make that computation. So in conclusion, to build stage discharge curves, which can be used to take stage-only data and make discharge data, we need measurements at different stages and flows. It's not useful if you keep going back and making a discharge measurement at the same stage all the time. You need discharge measurements at different stages so you can build the stage discharge curve. We are looking for careful workers to learn how to make discharge measurements using the BLM Fort Stanton Cave Study Project current meter outfit, so that there's a team that can go down there at different flows and make discharge measurements so we can start building stage discharge curves. We need measurements both in the cave and for surface streams. Thank you for viewing our presentation, and we will be available later today during the question and answer session if you have any questions. Thank you very much.